welcome to this really exciting panel. I'm very happy to be moderating today. My name is Sahba Al-Shawa. I'm the founder of the Jordan Space Research Initiative. We work on bridging space with sustainable development, which is also what I'm researching in my PhD, space and sustainability. So I'm very happy to be talking to these experts today about space-based solar power, which, if you don't know, is a really fascinating field and has a lot to do with sustainability. So I'll let each of our experts introduce themselves, and then we'll dive into the discussion, and we'll have a bit of time at the end for Q&A. So if you have any burning questions, hold on to them, and we'll get to that in the last 10 minutes. So Naoki, we'll start with you.
So, hello, I'm Naoki Shinohara from Japan, and I'm a professor of Kyoto University. Please don't confuse. In Japan, there are two similar cities, Kyoto, Tokyo. Tokyo is a current capital, and Kyoto is an old capital in Japan. And I'm a professor of Kyoto University, and my research topic, my major is wireless power transfer and SBSP from my student time. So about over 30 years, I spent my research life for SBSP and wireless power transfer. So thank you so much.
Good afternoon, everyone. My name is Sanjay Vijendran, and I'm from the European Space Agency. I lead the Solaris Research and Development Program for space-based solar power, which is a new R&D program at the Space Agency to try to mature the feasibility of space-based solar power as a concept, as a technology that we can use, hopefully, to help mitigate the climate crisis. So I've been working originally in Mars exploration, has been my background for almost 20 years, but in the last couple of years, I've turned to space-based solar power because I see this technology is really promising for helping use space to mitigate the climate crisis in the short term better than we are already doing now.
Good afternoon. My name is John Mankins. I've also been working in the field of space solar power like Shinohara Sensei for just about 30 years. I was, for a number of years, the lead at NASA for their studies on space solar power from the mid-90s to the early 2000s. I've been involved in various international activities to advance the goal of space solar power, including the International Academy of Astronautics, the International Astronautical Federation Space Power Committee. I've been supporting a wide variety of global activities over the last 10, 15 years, and looking forward to discussing these with you today.
Thank you all. So with that, I think a very good place to start, John, given your extensive experience in this topic, maybe you can tell us what is actually space-based solar power and what's the history of it and how it evolved?
So space solar power is a very simple concept. It's the idea that you can go to space near Earth, harvest sunlight there, and deliver it safely and efficiently to markets on Earth, in particular when the sun is not shining on the Earth or when the wind is not blowing on the Earth. So space solar power is a dispatchable form of renewable energy that can be sent when and where it's needed on the surface of the Earth. It was actually invented in the 1960s by a fine man, Dr. Peter Glaser, who's now passed. And the key technologies that Shinohara Sensei is an expert in, wireless energy transfer, were invented around the same time by another wonderful man, Dr. Bill Brown of Raytheon. Between them, Bill Brown and Peter Glaser came up with the idea of space solar power circa 1968. But when the preliminary studies were done in the 1970s, using the technologies of that era, the cost of deploying the first solar power satellite, as they're called, SPS, would have been on the order of $1 trillion because of the massive infrastructure that was required to even contemplate deploying such enormous structures. It's only been in the last 15 years or so as stupendous advances have been made in component technologies and in key infrastructures that space solar power has really come forward as a viable energy option. I think there's a lot more, but that's enough for now.
It's a good place to start. So maybe from there, Sanjay, you can tell us a bit about your work at ESA. You know, you're working on developing a roadmap for these technologies. Can you tell us what are the current projects worldwide and at ESA that are attempting to bring this technology to reality?
Sure. So this topic isn't new to ESA. Like NASA and other agencies around the world, ESA has looked at space-based solar power as a concept for decades and always come to similar conclusions as everyone else, that it was essentially an idea ahead of its time. It has always shown a huge promise. It was likely technically feasible with enough investment, but the economic case could not be closed in the past. So that was the conclusion of our most recent study into this area back in the mid-2000s, when we concluded this wasn't ready yet, but would likely be 20 years from then, when things would have changed with reusable launches, with mass production of space hardware, and then finally the economic case would be able to be closed. So we are pretty much 20 years since that report in 2005 that we did. And indeed, that's exactly what has happened. We've seen the advent of reusable launches, we've seen mass production of satellites for telecommunications. All of these key factors that were the economic roadblocks to space-based solar power have started to fundamentally change. And so now ESA's decided with our Solaris program that we initiated end of last year was the time to really do an intensive study, not take too long about it because we're trying to help with the climate crisis, so there is an urgency there, but to spend 2 or 3 years to really look into the technical feasibility, the business case, the political aspects, the regulatory aspects, the social aspects, to try to answer some of the many questions that have been thrown up over decades of study, so that we can make a really informed decision in 2025, 2026, a few years from now, on whether to go ahead in Europe on a full development program. Now, we know others are moving ahead on this technology around the world. China has a declared program to put space-based solar power satellites at the gigawatt scale by 2050 into orbit. The UK is very active in this area. The UK government has a big push towards space-based solar power as well as part of their energy policy for the future for net zero. There are actors in the US like Caltech and the US military that are working on it. So there's a huge acceleration going on now with a number of programs all around the world. But yet it's just the beginning, and there aren't any really big, well-funded programs intensively enough to take this forward right now. So part of what we're trying to do at ESA as well is to raise awareness about this topic, because the energy sector, who are the end users, the customers who should know about this and help deploy this, are simply unaware of this potential technology. It's been stuck in the space sector for far too long as an esoteric idea, but that bridge across to the energy sector and the national government ministries working on energy policy, they're the ones who need to know about it and soon start to support it with the capital that they have and the policies that they have to push renewable energy.
Yeah, that's a really great point. I think in the space industry in general, awareness is one of the key things that we need to tackle. And we see this a lot in Jordan, for example. Even the idea of going to space is seen as a waste of time, a waste of resources, but that's because there's this lack of awareness of what space could actually bring back down to Earth, and this is definitely one of the key examples as well. So Naoki, you're involved a lot with wireless power transfer. You're one of the experts on this topic. Can you tell us a bit about the technology readiness for this as well as the market readiness? What are the things that are actually going to enable this technology to happen?
Yeah, thank you so much. So I think to realize SBSP, we need a lot of innovative technology in space. Of course, we need a low-cost launch or huge solar cell technology or large infrastructure in space and wireless power transfer, I think. Fortunately, we have a technology of the solar cell in space, of course, you know. And so we have a low-cost launch system, mainly in US, SpaceX was the other. And we could build International Space Station, and we have a good technology to build large structure in space. But only one exception is wireless power. Maybe you know there are no wireless power transfer commercial market in the world. So I focus mainly on the research of the wireless power transfer as a professor of university. And before the solar power satellite, before realizing the SBSP, I think we need a new commercial market of the wireless power transfer. And this is only a tiny step towards SBSP, but this is a very important step to realize SBSP. So fortunately, recent 10 years, new market of the wireless power transfer arise now. So for example, today, around there in Dubai, we have a big conference to discuss about the new regulation of the radio wave application, including wireless power transfer, named WRC, World Wireless Communication Congress. And in this WRC, we have a hot discussion about a new regulation or a new commercial market of the wireless power transfer. And in US or in Japan, there are some interesting startup company to promote wireless power transfer now. So step by step, we would like to establish a new technology of the wireless power transfer towards the SBSP, like a low-cost launch system or infrastructure in space or the other. So this is my research, and this is my expectation towards the solar power satellite from the business side.
That's really interesting. And just to kind of bring it back also to applications that we're familiar with, you know, wireless power transfer at the basic level. I know my phone can charge itself wirelessly, right? But when you're talking about this large-scale application, what are the challenges that come with actually doing it on that scale?
Thank you so much. So I think we need two innovative technology to promote wireless power transfer, not only for SBSP, but also the commercial application. One is a beamforming technology to focus almost all wireless power to the users. And so this is most important technology for solar power satellite and commercial market, commercial technology, because we have to increase the efficiency of the wireless power, and we have to avoid the human body to protect us. And we need a very innovative beamforming technology. But in 20th century, unfortunately, there was no market of the beamforming technology except the solar power satellite. And recently, we have a market, a new market of the wireless power transfer, additionally remote sensing. So I expect this technology. And the second one is semiconductor. Of course, we all need a very good semiconductor, not only for wireless power transfer, but if we consider the energy, efficiency is most important factor. So unfortunately, recent semiconductor is mainly for the wireless communication or the remote sensing or the other, only for the very convenient technology of the radio application. It means they don't mind mainly efficiency. So we need a very excellent semiconductor, FET, HBT, or the diode for the wireless power transfer. And if we can create a new market, so new semiconductor, novel semiconductor will be born. And unfortunately, in 20th century, there was no market to promote development of the new semiconductor, unfortunately. But recently, new market of the wireless power transfer arise, and we can expect the new technology of the semiconductor as a power conversions. So I think these two technology we need and we can expect for solar power satellites.
Yeah, it's a really great point. Other than the technology itself, it's also the demand for the technology and the need within the market. And John, you also mentioned, this technology or this idea has been around for a long time, but it was very much not feasible economically back then when it first came up. What do you see as having changed now that could actually enable us to achieve this?
So from my perspective, granting the critical importance of the technologies that Shinohara-san mentioned, it really comes down to economic viability and to the cost of the system. And so as long as a space system costs $100,000 a kilogram, and the rovers on Mars cost $1 million a kilogram, then large-scale commercial activities in space are impossible. And what we have seen, which Sanjay alluded to a few minutes ago, is a transformation in space activities due in part to the mass production of really rather nice, simple but effective space systems. The massive number of engines on a Falcon 9 heavy lift. It's 27 engines. Those are all mass-produced engines as well as being reusable. The large-scale constellations in low Earth orbit. Hundreds of satellites, thousands of satellites coming off of production lines. Unimaginable 10, 15 years ago. Independent of the hopeful prescience of ESA studies in 2005. Frankly, having worked hard on this for a long time, nobody envisioned this as being a breakthrough for space solar power. The big change, for me, the big transformation, was in the modular architectures, making solar power satellites out of many identical pieces that can be produced in factories, and the emergence of the robotics that would allow these to be assembled autonomously without the presence of huge factories or thousands of astronauts. And that's what changed the situation from the 70s through the 90s to the last decade. It's all the things we've talked about, but especially these hyper-modular architectures that allow the solar power satellite to be made in factories like consumer electronics and get cost per kilogram of hundreds of dollars, not hundreds of thousands of dollars. And it makes all the difference.
Yeah, that's a really great point. I think in most space systems, this idea of modularity and being able to produce it in a sustainable way. So bringing this back to sustainability, I think there's two kind of different areas we could discuss, which is how it helps with sustainability on Earth, but also the sustainability of the technology itself. So first, with Sanjay, can you tell us a bit about the potential that this has, not just with, when I say sustainability, it's a multifaceted thing, right? Sustainability isn't just reducing carbon emissions, it's creating really a sustainable system, and also the role of international collaboration and emerging space countries and key players. So how can this technology help us progress in that direction?
Thanks for the questions. Quite a lot in there to unpack, but okay. So as a sustainable energy source, I would argue that space-based solar power is the ultimate sustainable energy source. It's our fusion reactor that's in the sky there that is guaranteed to operate for the next 5 billion years, producing energy that's right there for the taking for us. And solar power is fantastic, I think we can all agree, but we're not tapping that resource in the best possible place for it. So when you think about space-based solar power, putting your solar panels up in space where the sun is available 24/7 at its most intense form as well. It's the purest form of purest form of solar power. You can think of it as just more advanced form of solar power than we have on the ground. And so being able to tap this resource where it's most available, continuous, and highest intensity has got to be the best way you could possibly do this from a technical point of view. Of course, there's the issues of how can we do it economically, and there's a lot of consideration about making it cost competitive. But that is the place to go and get this energy, and it's going to be available for a long, long time, and it has the potential to be a scalable source into the future. And this is an important point when we think about new energy sources, is we have to have scalability to the large volumes of energy we'll need, not now, just the next few decades, but into the future of humanity on Earth, that new energy source has to be scalable. And this is where space-based solar power has huge potential, because there's a lot of room up in orbit. You can put up, theoretically, if you have enough time and engineering, put up thousands of these power plants that can provide a good fraction of the world's energy needs in the long term. But sustainability, contributing to that sustainability on Earth through providing this vast amount of affordable green energy 24/7 is one thing. We also have to make sure that it's sustainable in space. And you've all probably heard about the issues with space debris right now, space sustainability. So there's two aspects with space-based solar power. You have these very large structures that are, of course, going to be not immune to being hit by debris that's up in orbit. So on the one hand, we have to make sure that we can be resilient to the inevitable collisions with small particles and even larger things floating up there. But we don't want to be the source of many more pieces of debris either during the lifetime of these structures. So there's a huge challenge with dealing with both of these aspects, which we haven't solved today, but they're recognized, and we definitely have to make this sustainable in space in the long term, including at the end of life. So getting rid of satellites of that size cannot be through burning them up in the atmosphere or just leaving them in an orbit where it won't interfere with something else. We're talking about thousands of tons of material. So at ESA, we're already thinking about implementing the circular economy, not only zero debris, but the circular economy in space, where we can imagine decommissioning these satellites, reusing, repairing, recycling in space in the future. So that's a key aspect as well.
Yeah, that's a really interesting point.
About the sustainability, I have one comment. We Japanese once estimated the energy payback time about the SBSP. Energy payback time means, of course, we need more material energy or the other to build everything, including SBSP. And after building the SBSP, we can generate the power or electricity. And the ratio of the input power versus output power, and so how long we can recover the total energy which we used. As a result, only 2 years we can recover all energy which we use to build the SBSP as a result of the new power generation. Only 2 years. If we put the solar cell on ground, unfortunately, this energy payback time will be extended. And I have the one more comment. Maybe you know the limit to growth, a very famous simulation and a book about to describe the limit to growth on the Earth. And they revised the third time, and the result is the same. We have a limit to growth on the Earth. But in 90s, one Japanese professor simulated this same global simulation, including the SBSP. And as a result, by his research, we can overcome the limit to growth if we will build the SBSP. So this is exactly the same as a simulation by the Roman club. Exception is only the SBSP parameters. So I do believe we can climb up, we can overcome the limit to growth, even if we have a SBSP in future.
Yeah, that's a really interesting point as well, kind of the trade-off, right? Because anything that you build, any system that you launch also has environmental impacts. But then if the benefits outweigh the cost, then it does justify, sending it into space. But another really interesting point that you brought up, so for those who don't know, the way that right now you deorbit a space structure, essentially it just comes back down to Earth and it burns up in the atmosphere. And this is something that ESA is also trying to characterize, because we actually don't know the impact that has on the climate. It's still an ongoing kind of discovery. So there's also this question of the unknowns, the impacts that we don't even know yet. And so I wanted to go back to also the idea of sustainability in space. John, we know each other from the Moon Village Association, so I want to bring it back to lunar exploration. How do you think, exploring the moon and this technology go hand in hand, and what are the ways that actually lunar exploration could support the development of this technology?
So the essential idea here is not so much that a solar power satellite is a new kind of solar power plant, and that after 15 or 20 or years, you're going to decommission it, as Sanjay mentioned. These are going to be enormous systems. They're going to be almost like new moons in Earth orbit. And as a circular economy, or with the recycling of the piece parts, these platforms will essentially provide energy to markets on Earth forever. So they don't have a finite life. When you launch 1,000 tons of aluminum, you don't lose it because it gets damaged, or it can be repaired, it can be recycled, reforged, make a new structure, put it back into the system. Now, by developing space solar power systems in this way, with an eye towards recycling and refurbishment, you introduce the opportunity for the piece parts of space solar power systems, solar power satellites, to be gleaned from, for example, the moon. The moon is almost entirely made up of the molecular piece parts, the aluminum, the silicon, iron, that you need to make a solar power satellite. And so if you establish an economy in space that is a circular one, where you can basically remake these materials as they fail and refurbish and repair, you can also expand and extend the energy that you harvest in space for Earth using extraterrestrial materials. Now, this doesn't happen in the near term. This isn't going to happen in the next 5 or 10 or 15 years. But nevertheless, by looking at the future with a long view, you can develop solar power satellite systems that lend themselves to then getting a larger and larger share of their mass, until the point by later in this century where literally thousands or at least hundreds of gigawatts of completely carbon neutral energy can be delivered to Earth from platforms that were made with materials from off the Earth. And this is sort of the ultimate in balancing the competing interests of a sustainable future for the world and an equitable and prosperous and high quality of life future for humanity. And this is one of the visions that stimulates those of us who are in the field of space solar power and have been for many years.
Yeah, I think that's a great point as well about the equity and the inclusiveness of space. I think especially with lunar exploration, we're seeing now a lot more countries are getting involved in this direction. And historically, space has been more or less dominated by a handful of very strong players in that field. But now you can see even, with the UAE or Saudi Arabia, or even countries like Jordan that don't have a space program, are all contributing in different ways. So what are some of the ways that emerging space players can contribute to space-based solar power, given that it does have this extensive history? Where are we at now that people can come in and contribute their expertise to help it grow? And to anyone who would like to take that question.
So of course, now it's a Japanese case. As you know, Japanese economy is now it's very weak, and we don't have enough budget. So in both meaning, we would like to apply the SBSP technology, mainly wireless power transfer technology, to the lunar moon base. And from the gateway orbit around the moon, now we have some feasibility study to apply the wireless power from the gateway to the moon or on the moon. Maybe we can apply the wireless power transfer to drive the moon robot or the other. So I think spin-off technology of the SBSP can be applied to excite or encourage the moon technology or the moon research. This is a Japanese trial. And I think both we need a lunar technology on the moon and SBSP technology, because it's my viewpoint. So I think SBSP is very huge space technology, over 10,000 tons or more, but this is a very small technology. If we consider the space colony or Mars immigration or moon base or the other. So both meaning we need SBSP technology as a renewable energy on the Earth, or new innovative space technology to the future, Mars immigration or to develop the space colony or the other. So SBSP is, I think, it's very, very important technology as a bridge between the small satellite technology to the moon base or the Mars immigration, I think.
If I may add to that, I think there's a number of ways that emerging countries, space countries, can play a role here. The one aspect is the technology, where there's a lot of relationships with technologies of interest on the ground as well. When we talk about the solar technology for space-based solar power, this could be ending up being a spin-in from our investments on solar cells on the ground, with the new kinds of materials that we heard about earlier today as well, being invested in mass production, low cost. This is all things that are needed for space-based solar power as well. And for the energy transition, many countries which are emerging space actors also happen to be big energy actors around the world with the capital, with the motivation and interest and expertise to extend those new technologies and extend their sphere of working in the energy sector into space energy as well. So they can bring something to the table from a technology point of view. But there's also the aspect of governance and international cooperation. To do something like space-based solar power is going to need to have new agreements in terms of regulation, health and safety standards, and just how we go about as a global community implementing something that is going to be a global infrastructure eventually. It won't be power plants just for one country. It has the capability, like satellite communications, to provide power, depending on which orbits you put your satellites into, to different customers all around the world. So here, small countries even could have a role in taking the lead to try to bring the world together on this topic of space-based solar power, because at the moment, the efforts are relatively disparate. They're not federated, but that's going to need to happen in the future. So as we've seen with space resources, for example, a small country like Luxembourg has played a huge role in being a focus and center in bringing the international community around a new topic together, despite their relatively small size. And something like that could easily happen, I think, with space-based solar power, where a country takes the lead and doesn't have to be the one that's producing all the technology or producing the systems, but internationally has a role and has that foresight, future thinking to see this is something for the world and we want to help make that happen.
So just to bring it back around to the example of lunar exploration and lunar activities as a way of anticipating what is likely with space solar power. So of course in the 60s, it was the race between the superpowers, the then Soviet Union and the US, two superpowers competing for space, competing to go to the moon. Fast forward 30 years to the late 90s, and you start seeing space activities in Europe, which have matured over the previous 20 years. In Japan, you start seeing missions to the moon and to the planets from a handful of countries. And then today, with the intense international interest in the moon, there are literally dozens of countries that are involved in activities having to do with lunar science, lunar research, lunar exploration, lunar development, and this and scores and scores and scores of private sector players that are playing really critical roles in the push for the new technologies. So now take that as an example of how space has changed since the 60s, 70s, 80s, 90s to now, the 21st century, to the 2020s, going into the 2030s, I think it is inevitable that smaller countries, especially given the modular character of the most successful solar power satellite concepts. When you've got an object that's basically a 12U CubeSat, if you know that jargon, anybody can make it. And I think that's one of the reasons why Luxembourg was able to step in with a relatively small investment, because then the companies that responded were doing asteroid exploration missions with missions that weighed 100 kilograms, 200 kilograms. It doesn't take an industrial giant. It takes innovation, technology, investment, and the framework in which small technology plays can lead to huge investment gains.
Yeah, wonderful remarks from all our panelists. I think, as you're saying, there's a lot of potential here, but we really need to come together and push for it to happen. So with that, I think we have time for 2 or 3 questions. I see your hand went up first, so.
Well, I think, excellent session. First of all, congratulations. But more than cooperation, I like competition. And the fact that it's not just the USA, that Europe is coming into the game, Japan is coming into the game, and now China. China has announced plans for the 2030s. And now there is even more competition from the private sector, which I love, because it was Elon Musk who disrupted the normal space industry. So I have seen a few companies coming in the USA and in Japan. So I want to hear about which companies do you see, because I was in London 2 months ago, and there was a company saying that in 10 years, between 8 and 10 years, we might have a space solar power here on Earth.
Does anyone know any specific companies, private entities working towards this?
There are several of them represented here in this room. So certainly I'm one of them. Certainly Martin Soltau is here from the Space Solar Limited is another one. There may be others, I'm not sure. But so there are a number of players right now. It is all going to come down to ultimately the cost of launch. And so, and what you see now, which is a complete transformation, all driven by SpaceX, although I give more credit to Gwynne Shotwell, because she keeps the buses running on time. But nevertheless, now, whereas 10 years ago, there was no program in low-cost launch. Now there's SpaceX developing their next one, there's Blue Origin, there's developments in Japan, there are developments in New Zealand, for goodness sake. In the European Space Agency, the protein effort to put together a low-cost launcher, in China, and on and on and on. This is a revolution. And so I think, to answer your question, there's a lot of players, a couple of them here, but the key question is not who has a nice idea for a solar power satellite. The question is, when do we start getting launched to Earth orbit at less than $1,000 a kilo? And I think that's coming fast.
I disagree, John, that there are a lot of players. I think there should be far more players in this area, given it's
just more than there ever were before.
Yeah, absolutely. but there are actually too few players. Given the potential of space-based solar power and our need for it in the near term, there's far too few players. I mean, if you compare to fusion, which is receiving huge amounts of private funding as well, on top of the government funding, and there's a plethora of startups in that area, there's nothing like that yet in space solar. And we've talked to investors in Europe and beyond who have capital to invest in space solar, but don't have people to invest in, because there's just not enough companies in this area yet. And that's because they haven't had the public sector provide a perspective, a vision towards this being a technology of the future to give them the confidence to get into the field. So this is why through the European Space Agency Solaris effort, we're hoping to try to stimulate this ecosystem in Europe at least, but that's going to help and beyond as well, to grow these companies so that the private capital can go into it, because people have money to invest. They just need people to start getting into the field. So any entrepreneurs in the room, this is the time to get into this area. I won't mention any other names because I don't want to be accused of missing out any companies, but we can have a private chat about that later.
I was just wanted you guys to circle back to talking about fusion energy. So I was wondering if there's some sort of collaboration that can happen between space solar power and fusion energy, because as we've been seeing the past couple years, fusion energy has been maturing. They did reach a break-even point in California, I believe, last year at one of the labs. So I was just wondering if there's like a potential collaboration between the two energy sources for a more diversified and sustainable power grid.
Okay, so probably not. So the dilemma is, of course, that fusion power, when it comes, probably in about 20 years, but I've said that for 25 years, so. But that's just being snide. But fusion power, when it comes, is going to be a lot like fission power. It's a fission power plant. You start it up, and you run it for decades, and you very, very seldom shut it down. And that makes it a relatively poor fit for the features that space solar power can bring to the table. A much better collaboration, in fact, the ideal collaboration, will be between space solar power and ground solar power. Because ground solar power has regular outages that vary with time. They can be forecast normally weeks or days in advance. There's certainly seasonal variations. That's when you put in as much solar as you like in Berlin, you're still going to have almost no solar power generated in Berlin in December. But you could have a lot of solar in Germany and have space solar providing the solar power when the sun's not shining for weeks at a time. That's good to get these curves that can be complementary, and that's the ideal collaboration. So, but fusion is a big plant. You start it up, it's just going to, if it runs well, it's going to run for decades, and you don't want to shut it down.
I'm going to combine my question with George as well. It's Fiona Bannister. So I've been a small investor in ARC Nuclear and small SMA Nuclear. And so this has a place and a role as we go further into space. And also, I stopped investing into solar in 2012. But the core that came out in deep decarbonization is how do we bring the minerals from the moon to actually mitigate and provide, as you said, the solar that we need for our energy resources. I'm going to pass that on forwards to George for a minute.
Well, I'll let you answer her question, but just wanted to say that Blue Origin's in the room. So I'm from Blue Origin, and we are very excited about many possibilities that can be developed in low Earth orbit or higher Earth orbits, and lunar resources we do think will play a big role in lowering that cost so that you don't have to bring all the resources from Earth. You can bring them from a much lower gravity well, or easier gravity well, which is the moon. So I'll say that just kind of as a simple statement. There's a lot of things going on with our architecture to make lunar resources easier to use, and I hope that will factor into y'all's calculations, and we look forward to bringing that launch cost down for you as soon as possible.
Any comments?
Make a point about the mineral. I'm glad you brought that up about mineral usage, because that is one of the concerns with the energy transition. And when you think about it, with ground solar, there's vast amounts of minerals that are used, but then not used most of the time because of weather, day-night cycle, and things like that. So this is where space-based solar power has a huge advantage in the sense of using the mineral resources, the precious ones we've mined out of the earth, far more efficiently, because one thing that hasn't been mentioned here is that we're talking about power plants with very high capacity factors, meaning that they operate most of the time, more than 90% of the time. You can have power being produced by this solar power plant, and so therefore it's a very efficient use of the minerals. But nonetheless, it is still going to require, if you scale up space-based solar power to large numbers of satellites, large amounts of minerals, and this is where, again, to John's point about the use of lunar resources, to get those minerals from the moon rather than from the Earth, both reduces the cost and the environmental impact on the Earth itself by doing it that way. So that's a key consideration.
Okay, I think we're out of time for questions, but I will let the panelists leave you with one last remark. What is the main thing from the conversation today that you really want to stress and leave everyone here thinking about after this panel? And of course, you're free to catch them afterwards.
So I was I enjoyed a lot to be here and to show our research activity of the SBSP. So someone mentioned we need international collaboration and competition towards SBSP, and I do believe SBSP is a very excellent technology, but it's a very future technology. So we need once commercial market, and next the middle size of the SBSP as technological evidence or the other, and step by step we create the SBSP by the technological side. So I really appreciate to join this discussion, and I enjoyed it. Thank you so much.
Thanks. I just want to say I'm really pleased to see this conversation happening in this new part of the world for SBSP, which has not been a place where we've had these discussions before. And for a region of the world which has been so connected for so long with being a major player for energy in the world, I think it's absolutely important and right that this conversation is happening here. And I would say to the people from around here who are from the industry, the energy industry in the Middle East, that I think the future is about drilling up, perhaps more than drilling down. And so there's a big energy source there available to be exploited, and I hope that it gets the attention it deserves in this region going forward. And I'm really pleased to see at COP28 on Sunday this week, it's going to be the first time there's going to be a panel in the green zone on space energy. So it's fantastic that the conversation is getting out to a wider and wider audience now.
So I will, of course, echo what the others have said about what a pleasure it is to see this level of interest here at this future forum. I want to highlight one aspect of space solar power, though, and that is that although it is a truly game-changing concept, none of the basic physics is novel. All of the basic physics have been used since the beginnings of the space age. Every time you make an internet connection using a Starlink, or watch TV from a broadcast satellite in GEO, or any of those other things, all of the physics in that technology is the technology you need as the physics for a solar power satellite. So the systems are novel. There's a lot of engineering to be done. Notwithstanding Shinohara Sensei's correct assessment of the state of the technology for wireless energy transfer, nevertheless, the technologies to pursue space solar power are not so far away. And one of the things that I would encourage is a change in perspective. And just to leave you with that thought, that it's not a question of doing huge system studies and huge paper studies and huge research efforts until we end up with the perfect solar power satellite. It's more like an USB drive, where you start out with one that's only got 126K, and then every couple of years you update, you upgrade, you revise, you improve, until today you can go in for a couple $100 and buy a quarter of a terabyte that you put in your pocket. And that was unimaginable 10 years ago. 20 years ago, it was worse than unimaginable. So please think of space solar power as something where you get in, you get your hands dirty, you start building stuff, and that will be the way to make progress more quickly. Thank you.
Thank you. Thank you, everyone, for joining. I will also mention that ESA brought some flyers about their project, so catch them before they run out. And yes, thank you again to all our panelists. We really, I hope, learned a lot today. And feel free to catch them after the session. Thank you.